Okay.
Could you do a quick example on like oxidation, burning, or combustion, like the ones you gave us in the
That
lab?
reminds me. Yes, that does remind me. Combustion reaction, right? That's the one
Yeah.
thing that I said that I would go over. Thank you. You're awesome. I'm going to give you 2 examples. Okay. Let's see. Oh, you guys, this will be great. Let's go. Okay, propane. What does propane look like? What is the chemical formula for propane? What would be the stick structure for propane?
Would be like an arrow.
Okay.
So would it be CH3?
Would it be CH3? How many carbons?
Oh, so 3.
3 carbons. Then if this carbon, let's just draw C, then how many hydrogens would be around here?
3.
Okay. Oops, that's right, hand upside down. What about here in the middle?
2. Yeah, I don't think we ever went over that. I was going to ask you about that too. Is it always 3 on each end, basically?
Yep. It's saturated. Okay. Remember, we talked about it, but we didn't go over it.
I don't think we drew it out this way at all.
Yeah.
Okay.
I was being lazy.
Wish I could use that excuse on my homework. Okay, so then we have 8 hydrogens.
Okay. Okay, and that's reacting with
O2.
And it's going to make, anytime you have a combustion reaction, anytime you have a oxygen reacting with a hydrocarbon or an organic compound, you're always going to get CO2 and water. Okay. So, can you balance this? If so, how? Let's see, since everybody's talking so much today, it must be a Monday. I'm trying not to get upset on a Monday. Alberto, how you been?
Good. I'm just doing it. So
Okay.
you said you put a 3 for CO2, right?
3 for CO2.
Yeah, and H would be 4. Let's see. And 6, 10. And then for 5 for O2. Oh, for O2.
For O2, okay.
And then 4 for water, H2. I think.
Okay. So let's see. That's 10. Oops. Sorry, that's 8. That's 8. That's 6. That's 10. That's 10. Okay. Looks good. Simple.
Yeah.
So the hardest thing is remembering that anytime that you have an organic compound, you're going to end up with carbon dioxide and water. And both of these are going to be gases because, you know, it's burning. Okay, questions, concerns, Cash?
Is our propane also considered a gas? Yeah, right.
Propane is a gas, yes.
So I have a question. I missed the last lecture. I feel like there's some stuff that I don't really know about. So I'm guessing that is there any kind of formula that we can use to find out how many of each atom there needs to be on both sides, or is it just like kind of guessing and choosing?
It's a little bit of guessing and choosing, but it's also I have a little method, right? So I look on both sides of the chemical equation, and then I look at something that it's only mentioned once. Like here, we have carbon only once. Then over here, we only have carbon mentioned only once, right? So then I would start off with that. And then I looked at over here, then hydrogen is only mentioned once. Here, hydrogen is only mentioned once. Then I do that one next. Then the one that has multiple mentions, we have oxygen, and it's in 2 spots. I do that last, because usually it works itself out.
So on the reactant side, are you saying that you just go from left to right in like whatever order the atoms are, the molecules are in?
No, I just I pick and choose, right? It's not necessarily from left to right. I just look to see, again, how many times do I see carbon over here on my reactant side?
Oh, so it's more so about like that's only mentioned once on the reactant side, but like oxygen is mentioned twice on the product side. That's where the difference is.
That's right.
Oh, okay.
And so I say the one that's more complicated for last, right? It's just
Okay.
kind of like, how do you guys do your homework or do your coursework, right? What I always did all the ones that I can get done fast first, because then you get them out of the way. And then I say the one that's going to take me some time, I do that one last, right? That's how I do everything. On the test, the stuff that I know real well, I just go through and answer all of that. Then I go back and work on the ones that are harder, because then you get more stuff done, you know? Right? And so it's going to be the same way in that sense. Does that help?
Yeah, that makes sense. Okay. Yeah.
Okay, good. So now I'm going to have, since Alberto was the lead man here, I'm going to have somebody else give me another. I'm going to change this to, let's do butane. Okay, so we're going to use butane this time. So what is the chemical formula for butane? Let's see. Cheyenne, can you draw me the chemical formula for butane and then tell me, or draw out the structure for butane and then tell me the number of carbons and hydrogens are in butane?
I'm a little confused how you got the carbon structure for propane even.
Okay, how would you find propane has how many carbons? Propane.
So it has 3. So then butane would have 4, right?
Okay, so butane would have 4. So let's draw 4 carbons. 1, 2, oops, and then we'll do 3 and 4. Okay.
And then do you just figure out how many H's are on there because carbon has 4
Good job. Yeah, 4 attachments, right?
Okay.
It has to have 4 attachments. So then
Okay.
we just put 4 attachments on there. 1, 2, 3. So that's the 4th one. 1, 2. All right. And then 1, 2. And then 1, 2, 3. So all of those would be H's.
Okay.
See, I thought you were making it sound like it was so hard. I don't understand.
Okay, so it'd be like C4H10, I believe.
Okay. Good job. Okay, so now we know. So if I want to balance this,
So
let's
you'll
see.
start,
Oh, go ahead.
oh, sorry. You'll start with the carbon, and since there's 4 on the reactant side, you need 2 for CO2.
You said since there's 4 on the reactant side, and then
Mhm.
we have 1 on the product side.
Yeah,
So then,
you need
how many?
2.
Would that give me 4? I put a C here. I'm not thinking.
Oh, wait, my bad. I was looking at O2. You
Yeah.
need 4, sorry.
Okay. Okay, so then that gives me 4. Oops. Okay, what about hydrogen?
And then you have 10 on the reactant side and 2 on the product. So you'll need 5 H2O.
Okay,
And
so then that would be 10 and 10. Then how many oxygens do I have?
and then you have 2 on the reactant side and then 8 plus 5. And then 13 on the product side.
Okay, so this is my only place for oxygen. So how can I get 13?
So can you like add another H2O or another CO2?
So if I did that, then this won't be balanced.
So then you would have to add another one on the reactant side as well. Can you do that?
No, because it's already set. This is what we have. We can't just magically, okay, we're going to put some carbon dioxide just for the hell of it.
So then would it have to be like a fraction?
It's going to have to be a fraction.
Okay.
So, but we know a fraction only works at what level?
What do you mean?
Does it work at the particular level? Can you have a half of a molecule?
Oh, no.
No, I can't have a half of a molecule, but I can have half a mole, right?
Mm-hmm.
Yeah. So it works at the molecular level or the molar level, but it doesn't work at the particulate level, right? So then because of that, we want this equation to work in both situations. We'd multiply this equation, the whole equation, by 2.
Oh, okay.
To get rid of that fraction. So then our final equation is going to be 2C4 H10 plus 13O2 8CO2 plus 5H2O. Okay, questions, concerns, Cash?
Can you explain to me the thing about the fractions? I don't understand that.
Okay, Kristen. Kristen, if I cut you in half, are you alive?
No.
Okay, so same thing with the molecule. If you cut a molecule in half, it's not a molecule, right? Because you can't really cut a molecule in half. It's dead in that sense. So that's the reason why we can't have a half. So then that's, again, that would be at the particle level, right? So the only way we have to have whole particles, we can't have fractions of a particle, right? So the way that we get rid of that fraction is by multiplying by whatever it's being divided by. So if this was ozone, which is O3, right? Then instead of having a half here, it would be 3 times that, right? To get rid of the fraction, you know? So then we multiply this whole thing by 2 to do that. Do you understand? Or I need to take a step back, one more step.
So are you saying that the 2 is in the denominator place to cancel out the 2 that's on the oxygen?
Yes,
Oh, okay.
yes,
So then you're just left with 13 oxygen atoms.
that's right. So that would give me
Okay.
my 13 right here. Yes.
That makes
Does that make
Thank
sense?
you.
Okay.
Oh, why did the
Mm-hmm.
O2 didn't multiply the water?
Oh, because I'm a bum. Thank you. Oops.
So when you said to cancel the 2 on the water, you mean like the subscript?
To cancel the 2 on the oxygen, and I'm talking about not the subscript. So like here, so because there's 2 oxygen, right? It's O2,
Right.
and so that we could have an odd number, 13, we'd have to multiply by 13 halves, because then that'll give me a total of how many oxygens? If I have 2 times 13 over 2,
Oh yeah. It would just be 13.
right? So then that'll satisfy what I need satisfied. But in actuality, it doesn't, because I can't have a half of a molecule, right? Have you guys ever seen a half of a person walking around? Right? You
No.
don't, right? Okay. So in that case, then you're not going to have a half of a molecule. So then we need to get rid of the fraction, and we get rid of the fraction by multiplying whatever that denominator is. Does that help?
Yeah. Will it always be 2 though?
No, it doesn't always have to be 2. If this was O3, like I said, if this was ozone,
Oh,
O3
got it.
here, then you'd be divided by 3, you know.
3.
Yeah.
Okay. Got it.
Okay.
Yes.
I have another question. Why are you multiplying the entire I don't know what the word of the entire reaction, I guess, but by a 2?
Why do you think we're multiplying the whole thing by 2? What are you trying to get rid of? Because I asked you this. Can you be a half of a person and exist?
I don't know what we're trying to get rid of.
So think about it here. This is 13 halves, right? So can you have a half of a molecule?
No, but I thought that just because that fraction is there, that implies that it's canceling out both of those 2, so then it's just 13.
But you still
Oh.
can't have a half of a molecule, right? Oxygen, O2 is a molecule. If you cut it in half, you make just that one. In that case, it will make that one oxygen, which isn't stable, right? It's kind of like cutting you in half, right? Do you kind of get that?
No.
Okay. O2 is this. In nature, oxygen alone only exists as O2. If you cut
Yes.
this in half, it's unstable. It doesn't exist, right? It's not functioning. It has to be in a reaction, or it has to be diatomic. Remember it, diatomics. Remember your
Yes.
diatomics.
Yes.
Okay. So like you, if I cut you in half, cut you down the middle, are you going to be functional?
No, I'm not. Maybe the thing is like, so, uh, how you rewrote it, like above the original problem, it's 1302.
That's correct.
So would that be 13 times 2,
Yeah,
which would make it 26? So that's not like an odd number. Is that what you mean?
Yes. Okay.
Oh, okay.
So if you look at it overall, right? If you look at the final numbers, the total numbers, that'll be 26. That'll be 26 on both sides. Up top, that'll be 8. If we look at it, that would be 8. And then here are hydrogens, that'll be 20 and 20, right?
Yes.
And then this would be 26 and 26 oxygens, right? And so it's balanced. So all we've done, because we know that we can't, at the molecular or at the particle level, we can't cut a molecule in half and half of a molecule, right? We can't do that. We need to have a whole molecule, right? So that's why we
That
multiply
idea
by two.
I completely understand, but I was more so like I was like just confused about like what like how it changed from the original problem to the rewritten one. But now that I know that's 13 times 2 and it's not an odd number, then that makes sense to me.
Okay. Sounds good.
Yeah, thank you.
Piece of cake so far?
Yes.
I have another quick question.
Okay.
For example, where it says 13 over 2 for the oxygen gas,
Mhm.
Would there be any instance it'd ever be O4 or like a different subscript on that oxygen? Is there any other, I guess, natural occurring?
No, so oxygen is a natural occurring element. You could have peroxide, right? Something with peroxide, and then the subscript would be different, and it may change the numbers. So there's a possibility of always changing that number, right? So like I told you could have ozone, O3, right? So if it was O3, then what would your number be?
Would it be 13 over 3?
That's right.
Okay, yeah. All right, you would definitely answer my question. Thank you. Perfect.
Okay. Are you guys with me?
Yes.
Nobody wants to jump off
Yes.
the boat yet, right?
Not yet.
Not yet. Good. Okay. Oops, wrong thing. Okay, so now that you guys know how to balance equations, now we're going to get to the nitty gritty, the bread and butter. I keep saying that, right? Bread and butter of chemistry. You're really now in the bread and butter of chemistry, right? So you know how to work with moles. You know how to work with balancing equations. Now we need to figure out what those moles are going to be telling us, right? Moles are quantity, right? You guys get that? It's quantity. Like when you think about a recipe, that's based upon quantity. Oh, I need 2 things of this and 4 things of that and 12 things of this. It's quantity, right? Yeah, no, maybe?
Yeah.
Yes.
Yes.
Okay, so since it's quantity, it allows us to sit there and use those coefficients to set up ratios with each other. So in theory, right, if I know how much ammonia, the quantity of ammonia I have, I can calculate how much oxygen I'm going to need to react with that ammonia, right? Or if I know how much ammonia I have, I can calculate how much nitrogen oxide I can make. Or if I have the number of ammonia I have, I can calculate the number of water I can make, right? All by ratios, right? And the way that we would do that is we'd use this as a guide. For ammonia, I need 5 oxygens, 5 to 4. For every 4 ammonia, I can make 4 nitrogen monoxide. For every 5 oxygens, I can make 4 nitrogen monoxide. And so I can use these to sit there and make fractions or factors. And I can flip them any way I need to, right? So as needed, so depending on what's given. So this gives me power, right? Gives me power to sit there and use those chemical equations as kind of like a recipe, right? So I can scale up or I can break down as needed. You guys are with me? How many of you guys bake cakes? Nobody bakes a cake?
Don't
Come
be
on.
expecting any.
Yes.
Everybody's made a cake from a box. Tell me that you have not made a cake from a box.
Have
I've made brownies from a box.
I baked a cake too.
You bake a cake from a box as well?
Yes.
Okay, so we have only 2 people who baked cakes before. Well, that's all right. You all are gonna make me my favorite cake. I'll be down in
A piece of cake.
piece of cake, exactly. I just want 1 piece. That's all I need. You guys can eat the rest. Just save me that 1 piece, okay? I will be down in Harnell in December. So I'm being interviewed for something. Anyway, so when you guys bake that cake, right? Tell me about it. Tell me what are the things that go into that cake?
You need just for a box cake, you just need oil and eggs and water, I believe. I'm not sure if you need anything else. I don't think so.
That's it. You're right.
Awesome. I don't know what moles are, but at least I know what goes into a cake. Just kidding.
Okay, good. Okay, so now, how many boxes of box cake do you need for 1 cake?
Just one usually.
Yep. So we need 1 box. Okay, how many cups of oil do you need for 1 cake?
Oh, I'm not sure actually. Is it like just 1/4? I don't know
I think
off the top of my
1/3.
head.
Oh yeah, 1/4 maybe.
A
I'm
fourth
not
of a
sure.
cup?
Probably, or 1/3. One of the two.
Let's go with the higher amount, and let's put butter there.
Okay.
Butter tastes so much better.
I like these subtle hints you always drop
You
about
lost
cake.
this now.
I'm just letting you know. I'm just subtle about it, Not
Yeah.
even, just little nidbits there. So we'll say 3/4 of a butter, stick of butter.
3/4?
Yeah.
Well,
of a stick of
yes.
butter.
Oh, okay. I thought we were still talking about oil. I'm just like, damn, this could be a really oily cake.
Okay. How many eggs?
3.
2?
I think it's 3.
It's
I'm
3.
gonna go with 3.
Oh,
I
okay.
think it's 3, yeah.
And then how much of I think is it 1 1/4 of a cup?
Um,
I thought it was only 1.
Okay, we'll go with 1. And I would put milk in there, but that would be just
Okay,
saying,
we'll keep
just
that in
letting you
mind.
know. What was that?
We'll keep that in mind.
Okay, so now this is the recipe for a cake, right? And let's say this
your
cake,
cake.
one cake feeds 5 people, right? Now, Brian and Cheyenne are getting married, and they asked you to make their cake, okay? And they're having 25 people come to their wedding. Congratulations, Brian, Cheyenne, 25 people.
So you need 5 cakes?
So how many cakes am I gonna need?
5 cakes?
5
Five.
cakes. How did you figure that out?
Just 5 times 5 is 25.
Okay.
There's 5 people, and there's for 1 cake, and
Okay,
there's
so
gonna
you
be 25
basically
people
did
there.
dimensional analysis, right? 25 people
Yeah.
divided by 5 people per cake. So can I tell you how many eggs I need? How many eggs are you going to need for Cheyenne's and Brian's wedding?
15 then?
Okay. So I can do that again because I know that 1 cake I need 1 cake, 3 eggs, right? And then I could do this for all of the others. I can figure out how many sticks of butters I'm going to need, how many cups of water I'm going to need, right? I can get it all worked out well in advance to make the 5 cakes for Cheyenne's and Brian's wedding, right? See, and I get to
Yes.
say, Cheyenne and Brian met in my class, in my chemistry class. And it was a connection at first, positive and negative, you know? You notice they're not saying anything, right?
I know.
Maybe they're trying to keep that a secret, and you just expose them.
I just blew it all out of the water, right? That's exactly what happened. Okay. Okay, so but you see how this works, right? It's real simple in real life, right? You use this all the time, don't you? At least I know I do. I'm like planning out a party. Oh, I'm expecting this many people, and don't you guys do that?
Mm-hmm.
hmm
Right?
Yes.
And especially when you're working on a budget, you're down to the letter, okay? And I know such and such ain't gonna come, so I'm just gonna make sure you're down to the letter. So it's exactly the same thing in chemistry, exactly the same, right? So don't let the chemical equation freak you out, right? It's the same process. It's a recipe, and then we're just using those numbers as guidance. Okay, are we good?
Yeah.
Mhm.
Okay. Okay. So, example, if 3.5 moles of, using that same equation that we just had, I'll have to put it up again. 3.5 moles of ammonia reacts, according to the equation, how many moles of water will be produced? So, go back to that equation. So we have 3.2 moles. Okay, using dimensional analysis or using our molar ratio, what is the ratio of ammonia to water? Let's see. You guys are so, Alexandria, what is the coefficient in front of ammonia? And what is the coefficient in front of water? Okay, that's all right. Alexandria is going to be having
Is
the
it
kid with the
4?
next. What was that?
Is it? I'm sorry. Well, I'm not Alexandra, but is it 4 in front of ammonia and then 5 in front of oxygen? You said,
Okay, it's
or you said water, right?
water.
Oh,
Ammonia.
6.
Okay, so if I want to get rid of the number of moles of ammonia and get the number of moles of water, what am I going to do? Am I going to put ammonia at the bottom, or am I going to put ammonia
At the bottom.
okay? So then I would put my 4 moles of ammonia, and that allows me to cancel this out. And then I put my 6 moles of water up top. And then this allows me to get the number of moles of water that I want, or that are going to be generated if I have enough of the oxygen available. Let's see. Okay, piece of cake. Cake.
I might need to
Yeah.
do it like, yeah, a little bit more practice.
That's all right. I got a lot of homework for you guys to do. I think it's about 100 questions. So you're gonna get a
Wow.
lot of practice. I promise.
And significant figures count for this?
Yes. How many sig figs? The only thing, oh, wait. Let me clarify. That's actually a good question. Who was that? Was that Alberto?
Yeah.
Yeah, that was a good question. So when you're using equivalencies or conversion factors, you don't use those to calculate your sig figs, right? So these guys kind of act like equivalencies. They're exact numbers. So you're not going to use those as your sig figs. You're going to use what's given to you as your sig figs. Does that help?
Yeah.
Okay. Good question. See, I like a man. He's already thinking sig figs. That is, whew, getting me hot there. Okay, that kind of went out, didn't come out the way it was supposed to come out. Let me take back that statement.
It's too late. It was already recorded.
I see that, yes. Okay. So now when we're looking to try to determine how much we can get from our reactants, how much products we can get from our reactants, we're going to use stoichiometry. This process is called stoichiometry. And you see it's spelled, it's a really fucked up spelling, you know, S-T-O-C-I-O-M-T-M-E-T-R-Y, stoichiometry, okay? Stoichiometry allows us to use those ratios to sit there and determine from the number of moles, how many moles of product we're able to produce. So from the number of our reactants, we can determine how many products we're able to produce. We can also work the other way around. From our number of products, determine how many moles we're going to need to make that, right? So it's kind of a good system once you have a balanced chemical equation. So first step is always going to do what?
Balance it out.
We're going to make sure that our chemical equation is correct and is balanced. That's always going to be your first step. So you should always verify your chemical equation. First thing always. Because if you have the wrong chemical equation, everything is going to be wrong, right? And doesn't that make sense? Right? Like if you guys were making that cake, right? And somebody said, oh, no. So we have a box cake. We're going to add 20 eggs to one box cake. Now, is that cake going to be right?
Nope.
No.
No, right? Or somebody says, okay, we have a box cake. You need to add 3 cups of salt. Now, is that going to be a good cake?
No.
No.
So you want to make sure that recipe is right first before you go on and try to use it, right? You guys get the analogy?
Yes.
Definitely don't make me a strawberry cake with 3 cups of salt, okay? Just letting you know.
Using reverse psychology there.
Okay, so how many moles of oxygen are required to burn 2.40 moles of ethane, C2H6? Okay, first step. Hector, my first step.
I'm not sure.
You're not sure?
No.
What did I just say, Hector?
To make sure your equations are balanced?
To make sure my equations are balanced. So the first thing I want to do we have an equation? Do you see an equation up here yet?
No.
No. So my first thing I'm going to do is what?
Find where your equation is.
Find what my equation is. See, look at that. I thought you said you didn't know.
Yeah, it's confusing
Okay.
at first.
Good. Okay, so now let's figure out the equation, you and I. Okay?
All right.
Okay, it says, how many moles of oxygen are required to burn 2.40 moles of ethane, C2H6? Didn't we just talk about burning stuff? Burn, baby, burn.
Yes, we did.
Yes, we did. So what was the chemical equation for burning? It's called, what type of equation? Alan, you want to help him out?
Combustion.
A combustion equation, right? Okay, Hector. So in a combustion equation, what is going to be one of the reactants here that's given to us?
Ethane.
Ethane, okay, which is C2H6, and we know that it's a gas. Now,
So I have a question. Sorry. So do we know that it's a combustion reaction because there's the gas there? Oh. Thank you
You're
for
welcome.
showing me what's right in front of me.
That's usually it is. You know, it's like when your mom used to tell you, if it was a snake, it'll bit you in the, you know. It's always the same case in chemistry.
Okay.
Okay, except for sometimes. Sometimes crazy things happen with the canvas shell. Okay, so what is the other reactant? Alan, help me out.
O2.
O2. One day I'm going to get Alan to be excited. Him and Hector. I'm going to get him so excited. Okay, so now we have our reactant, right? So I'm sure David is going to help me out with the products, right, David? Okay, that's all right. David and Alexandria are getting married, so that'll be my next couple there. Okay, Brian. You gonna help me out with those products?
Can I help you?
Um,
Oh, there we go.
the products are going to be CO2 and H2O.
Is the equation balanced?
No,
Okay, how can I balance it?
let's see here. Put a 2 in the CO2.
Okay.
Okay.
So that gives me 2 carbons. And I have what, 5 oxygens over here?
Yeah. Then put a 3 in the H2O.
Okay.
Especially.
So that gives me 6 and 6 here. And now that gives me what? Is that 7?
4. Yeah. So. And then a 3 in the O2, or 3 and a half.
A 3.5?
Yeah. Then multiply all by 2.
Okay. So wait, let's see. That gives me 3. Does that give me 7?
I think he meant 7 over 2, like
Oh,
not
7 over 2.
not 3 halves,
Oh,
3
okay.
and a half.
3.5. My bad.
Yeah.
7 halves. Okay, I get it. My bad. Okay. So, and then you said multiply everything by 2.
Yeah.
Okay, so then we'll get 2. We get 7. And this is 4. And this is 6. Is that right? Oh, 12.
Yeah.
Looks good to me. Looks good to you. Meet your approval.
Wait, but Why did you have, well, now it's all erased, but why did you have 3 on the reactant side on the oxygen?
Oh, because I thought he said 3. I thought he said 3 halves
Oh,
instead of, he meant 3 and 1/2. Okay,
so it's 7/2, right?
yeah, it would be 7/2, but now it's 7 times, and so then we'd have 14. Now, so that'd be 14. Okay, if my pen works.
Sorry, I was writing it all down.
What was that? Did it freeze? Can you guys hear me?
Maybe
We
your
can hear
pen
you.
ran out of ink.
Then Kristen got jokes today.
Yeah.
It's erasing, but it's not writing. Okay, hold on.
Maybe you're using white for the ink.
Ah, thank you.
So you tell West Hills to hire me for their IT department.
What is that? 12 and 12. Is that right?
Yeah.
Okay.
I think it's
Okay.
easier now that we know we can do halves and then multiply the whole thing.
What? Why did you put 14?
Because
Is that 14? That is 14.
it's 14. Yeah, this is a 14. Because 7 times 2.
Right, but wouldn't it? I thought it was like 7/2, so it would be.
It was, but we
7.
multiplied everything by 2, right? You didn't hear when Brian was
So
saying, because initially it was 7 halves, right? But to get rid of that half,
Yeah. Mhm.
we multiplied everything by 2, right? So we multiplied the whole equation by 2.
But I thought it would like cancel out the 2 at the bottom, not multiply the 7.
Okay, so it does both, right? Because if you have 7 halves, right? 7 halves cancels out that 2, but it doesn't really cancel out that 2 because can you really have a half of a molecule?
No.
No, I can't, right? And so you want a whole molecule, so that you never want to have you never want to have a half when you're talking about a chemical reaction, unless you're talking about a molar chemical reaction, high level. You don't know if it's a particulate or a molar, but you want to set it up. You want the chemical reaction to be set up so that you can use it under both circumstances. You don't want to do it special under one circumstance and not be able to do it for the others. Do you understand?
Mm-hmm.
Okay.
But you didn't do that for the other example. It just ended up being 13.
But yeah, it ended up being 13. Like this just ended up being 7 because at first it was 13/2.
Oh, like you just didn't multiply.
Yeah, I did the multiplication.
You mean like you just didn't multiply?
No, I did the multiplication. Only thing here, I didn't show you doing the multiplication. I didn't say, okay, we're doing this because he had just went through and said, oh, we just multiply by 2 to get this. And so I just wrote down what he said. Do you understand?
I think it's because you didn't write the balancing at the bottom on the last one is maybe what's being confusing. Yeah, you hadn't done that part on the last one, but
is it so it would be 7/2, right?
Okay.
Or
No. No. So initially, this is what it is. Okay, when we balance the equation, we get this. right?
Mhm.
Okay, so all I did
Yes.
was I multiply this by 2 because I can't have a half of a
Right.
reaction or a half of a molecule,
Molecule.
right? So then that gives me, if I
Right.
multiply this by 2, I get this equation above here,
Right.
okay?
Oh, I guess, okay. So is that our final product, right? On top, the light blue?
Yes, this is our final equation, our final balanced
Oh,
equation. And then you just want to
I
prove that
guess,
it's balanced, right?
okay. Because I guess I got confused because I thought you were putting like 14O2. Like,
Yeah, no, it's 14 oxygens. Because altogether, how many oxygens are here? Because we want to make sure
right.
that
Yeah.
at the
Yeah.
elemental level, we want to make sure that we have, or I should say at the atom level, we want to make sure that we have what we put in has to be what we get out. Because that's what a balancing equation does.
Right.
It verifies the law of conservation. What you put in is what you get out. Okay?
Right. I guess I got confused because I thought you were gonna put 14 as the constant in front of O2. That's why.
No.
Because I left it as 702. Okay. Good. Okay.
Okay?
Yes.
Okay, so now since you gave me such a hard time, you get to help me out with this. So the question asks, how many moles of oxygen are required to burn 2.40 moles of ethane? So what am I going to start off with? Now that I got a
So you
balanced
put
equation.
2.40 moles of C2H6. Oh, right? No, oxygen.
No, you're
No,
right. You're right. C2H6.
Okay.
Okay, but we want number of
And then
moles of oxygen.
so we put 2 moles of C2H6 at the bottom.
And then up top.
And then, sorry, my Wi-Fi is lagging, so it looks like you're not writing. And then at the top, we put 7 moles of O2.
Okay, what do you guys get?
8.4 moles of O2.
Okay. Oops.
So even though in my calculation I got just 8.4, I know the sig figs is 3.
Mm-hmm.
Would you just assume that the other one's a 0?
Yeah, because that's what it is, right? Because your calculator is only going to give you that number exactly, right? But you know that there's a 0 there, so you have to put that 0. You know what I'm
got
saying?
it. Yeah. Thanks.
Okay, questions, concerns, cash, cake. Okay, good. Good job, Vanessa.
Thank you.
Okay, so far we've been talking about moles, right? So if you're given mass, the first thing that you want to do is convert to moles, okay? Because moles are quantity. So I always like to think of it as moles is like the gateway drug, okay? You want to get to moles. Moles is that middle point, always going to be that middle point. Mass to moles. If you're already given moles, you don't have to worry about it. You're already there, right? But if you're given mass, you want to get to mass to moles. Okay, repeat that after me because this is the biggest mistake people make. Let's see. Repeat after me, everyone. Okay. If I'm given mass, I want moles.
I'm
If
giving
I'm given
mass,
mass, I want
Mass one
moles.
moles.
I want moles.
Say it again. Alberto didn't talk. David didn't talk. Hector didn't talk. Jennifer didn't talk. Okay, ready?
Yes, I did.
Yeah,
It
Hector
says you
talked.
didn't. According to my screen, it says nope. Jennifer did not talk. I have tallies. You know. Okay, ready? So if I'm given mass, I want moles.
If I'm
If you're
given
given
mass,
mass, I want
I want
moles.
moles.
Okay, good job.
did you hear me
That's the
now?
next tattoo.
I got you now.
Okay, I better
Yep.
get those points.
Okay. So now, here's the beauty of it, right? At this point, you know how to balance an equation, right? Once you got that equation, you can do so much stuff. We can start calculating solutions. We can calculate. I mean, there's so many different things that we can do now, right? You have just been invested with a great amount of power. You guys are, this is like chemistry gold right now, right? You've been blessed with this, okay? Now you got to utilize it, okay? And the best way of utilizing is by doing all your homework, okay? So if I'm given mass, I'm going to use the molar mass to convert to moles. If I'm given moles of my reactant, I can figure out how much of my product that I need. I can also figure out how much of my other reactant I'm going to need, react with it. I can then figure out if I need it to, I can figure out quantity. I can tell you how many particular products that I'm actually going to have, the particles, the number of molecules, the number of atoms, right? I can determine all of that by using that equation and by changing to my gateway drug of moles. Are you with me?
Yes.
Beautiful, beautiful. Okay. How many milligrams of nickel 2 chloride in a solution? Let's see. How many milligrams of nickel 2 chloride are in a solution if 5.3 milligrams of silver chloride is precipitated in the reaction of silver nitrate and nickel 2 chloride solution? Okay, what is the first thing I'm going to do? Jennifer,
Yes.
first thing I'm going to do.
See. Are given, which is all right, hold on, let me reread it. How many milligrams of nickel 2 chloride are in the solution, are in a solution if 503 milligrams of silver chloride is precipitated in the reaction of silver nitrate and nickel chloride solution? So we got to figure out the solution and balance it, or the chemical formula.
Okay, so what is the chemical formula?
Let's see. Chemical formula is silver nitrate plus nickel chloride. Then silver is Ag, nitrate. I'm looking at up my polyatomic ions. Nitrate is NO3 minus. So if it's, let's see, silver. Silver, when there is no Roman numeral, is it just automatically -1 +1?
It is, that's right.
Okay, so then that's balanced. All right, and then plus. Then we have nickel 2 chloride, and nickel is Ni. So if it has a +2, and then chloride is, oh, it's just Cl. So then it'd be NiCl2.
Okay.
Okay, and then the arrow So then silver chloride would be just AgCl.
And by default, what's going to be left?
H2O?
Do you see an H2
Oh,
in this?
sorry. Precipitated, just I started thinking of water. Be AgCl, and then would it be nickel, which is Ni, and then NO3?
Okay. Okay, so now we need to talk about S's and AQs and G's and all that stuff.
Those
So
are
what is
hard.
the state for the silver nitrate? Let's see, let's pick on someone else.
I have a
David,
question. Why aren't there two chlorines on the right side?
because silver has a +1 charge. And the silver have a +1 charge, for it to be balanced out, we only need one chlorine.
Oh,
So you got to look at it
okay.
independently. You don't just carry over on the other side. It doesn't work that way, right?
Yeah.
Okay.
Okay, that makes sense.
We use the coefficients to make up for that difference.
Oh, okay.
And that's why the coefficients are going to be important here. But David, tell me, what is the state of the AgNO3?
It's a solid.
AgNO3 is a solid?
Is it not kind of like a salt compound?
It says
No.
solutions.
Oh, so it's a liquid. AQ.
It's AQ. It's not a liquid, it's AQ. It's dissolved in water.
Yeah.
Okay. What about the nickel chloride?
Well, it's a solution too, so AQ.
Okay. Now what about the silver chloride?
Would we still consider it a solution?
You tell me, do I consider it a solution? That term
Yes.
precipitate means what to you? Or should mean what to you?
Oh, solid.
Solid. That's what I must have done. I almost started writing again in white. Okay, and then our last one is going to be, default is going to be AQ. Okay, now, let's see, Kevin, been kind of quiet. Is it balanced?
No.
No, so what do I need to do to balance it? Oh, and by the way, is this nickel here? Is this balanced? Is this chemical formula correct? Nickel nitrate.
I'm guessing no, since you pointed it
I
out.
think nitrate's a -1 charge, so you would need 2 of them.
I would need 2 of those, that's right. Okay, now we're ready to balance, right? So that could have been a big mess. So Kevin, you were telling me you're getting ready to preach to me, right?
Yeah, so you would put a 2 in front of the silver chloride.
Okay.
And then on the reactant side, you will put a 2 as well.
Okay, beautiful. Piece of cake? Anybody disagree?
I do. Just kidding.
Oh, okay. Okay, so the next step, Jason.
I mean, I know we have the 503 milligrams of silver chloride,
Okay, so
but
let's
I'm
start
not
off
sure
with that.
what we're going to do with it.
What are you trying to find?
We want to find the milligrams of nickel chloride.
So we want, you said nickel chloride, right?
Yeah.
Yeah. And we want milligrams. Okay. So how do I change? Because I can't use my equation until I change it to moles. So how do I change it to moles?
Mhm. Would we have to first convert it to grams so we could do moles per gram?
Okay, so we need the molar mass. So how do I figure out the molar mass? How do I calculate the molar mass?
You just add the masses of silver and chlorine because there's one of each.
Okay, so I've had silver. What is it? Where's my periodic table?
You don't have it memorized?
I don't have that one memorized.
Ooh.
Ooh,
Flashy.
dang.
I can tell you chloride. Chloride is 35.45. Silver, I
Oh, I
always
saw you
forget.
look at the table. Don't lie. Silver is
I'm
107.
pretty good. Okay, so silver is 107, 107.87.
So
So,
would we round on this one or would we not?
well, 107.
We get 143.32. I mean, I think we could round down to 143.
Okay. You say 143.32?
Yeah,
Are you sure?
unless I type something wrong. Hold on.
87 and 35.
Yeah.
I mean 45, yeah. Okay. 143 grams per 1 mole, right? Or let's talk about this because we're in milligrams, right? And you were sitting there, you were making that claim. So do we have to change to grams, right? Or if a millimole, if I put millimole over milligram, would that equal mole over gram?
Yes.
Yeah.
Yes. So long as I have that milli on top and bottom, that kind of cancels each other out. It's going to mean the same thing as having mole over gram, or I could even go kilogram, kilomole over kilogram. All right. Do you guys see that? So I can put, and don't tell my other class that I showed you this way because they're going to get mad.
They don't have to know.
It's our little
Yeah,
secret.
you can. Yeah.
Okay. So now we have moles of silver chloride. So if I want to figure out nickel chloride, what am I going to do?
We'll use our ratio from the equation.
Okay. So what is the
where
ratio?
Two silver chlorides
So is that on
equal
bottom or on
one
top?
on the bottom.
So 2 moles of silver chloride. And you said 1
Yeah, equals 1 nickel
mole
chloride.
of nickel chloride. Okay. So then that would give me, and actually we should say millimoles to be consistent. Milla and milla.
We don't have to change our coefficient, even though it's,
Milla?
yeah.
Long as you have
Doesn't-
milla on top and milla on bottom, you don't have to change your coefficient because then it would be the same. You're doing the same thing to both top and bottom. So it cancels each other out.
Wait, is MM? Did you say MM is millimole?
Millimole, yep.
There's such
Because remember,
thing?
you're using SI units, right?
Oh, I missed something. But keep going. I'll catch on.
This is from the very, very beginning of the class, right? Milli, right?
Also, okay, I see.
Okay, so then that gets my, let's get rid of, that gets rid of my millimoles of silver chloride. So now I have moles of nickel chloride. So what do I need to do next?
Now we
How do I
need
get
to
to gram,
find
milligrams?
our grams per mole for the nickel chloride.
Okay. So we know that nickel weighs what, 50 something?
58.96, 0.693.
58.693. So 58.7 would be okay. Plus, we have 2Cl. So what is that? So 2 times 35. 0.45.
$129.7. Will we just go 130?
29.7. Yeah, sure way. Why not? So we have on top or on bottom, 129 or 130.
We already put it on top, so
Okay, my head's not working today. Plus we're running out of time. Over 1 millimole. Okay, what do you get?
I got 228.64.
Yeah, I think you got a little too
I
much.
did it.
Yeah, 228, yeah, 228.64.
Yeah, because that's a 143 at that bottom, right?
So how many sig figs?
3. So 229.
Piece of cake?
Yes, now I understand why.
Okay. Okay, so questions, concerns, Cash, strawberry chocolate cake.
No, I think we're good.
Okay, good, good. Okay, so that's all I got for today.